Yeah, so this is a piece of work which I've been thinking about for a while with various different people who are listed on this screen, about how to deal with a question which came up earlier in this meeting, actually, with Rebecca Varney's talk. You know, when you have a very good, a very strong emergent constraint on some aspect of future behavior, but this is conditional on the ensemble you have, and ultimately, how do you deal with the question of how much do we trust the models which underlie that prediction, especially when model developers may say that there's some aspects of this particular relationship which is oversimplified. Over the last few years, I've done quite a lot of work on model weighting, and through CMIP's generations up till CMIP 5, various approaches to model weighting were proposed, and very few of them made any real difference to the range of proposed climate sensitivity, to the rate of proposed warming in the long term. And so this acted as a de facto reasoning for justifying the use of model democracy from CMIP in assessment reports like the IPCC. And in CMIP 6, this, as you all know, changed a little bit, because suddenly we found ourselves in a position where a lot of the models had a higher climate sensitivity than the previously understood range, and various papers came up with emergent constraints or indicators which suggested that the transient warming was able to distinguish between models which warm more or less in the future, and so it was now impossible. It's now impossible to get around the fact that model weighting is necessary. You can't simply. It's now completely clear that we can't just take for this ensemble at least, we can't take the model distribution to be representative of our uncertainty in future projections. So, so does this mean that we're now condemned to use emergent constraints for assessments going forward? And they offer a lot of appealing features. I mean, they allow us to constrain the future with some relevant part of an observable or relevant observable part of the system. But we're still learning as a community how to translate, if we find a constraint, how to translate this into a robust statement about probability for future projections. And we've come a long way. We've come a long way since in the last 15 years on this question. There's been a few very nice reviews over the last few years, which have said that we need to find out, if possible, we need to apply emergent constraints to different ensembles to test their robustness, and they need to be attached to a mechanism. But there's a further aspect to this, and in addition to this, we need to think about how to combine information from different emergent constraints, because we know in the real world that climate sensitivity, for example, comprises different feedbacks which combine together to make the total response. And so we need to find a way to extract the relevant piece of information which gives us the basis for understanding the feedbacks which combine to make the net system response. But there's a further aspect to this, and that is that the constraints can only be as good as the ensembles we have. And we can see, if we take lots of different constraints for climate sensitivity, which have been published over the last few years, aside from the question of whether the constraints are correlated, so aside from the question of whether they represent the same process in the ensemble, if indeed they're robust at all, or if indeed they're not spurious. There's the question of whether the real world lies on the line which is formed by two different emergent constraints. So you can imagine, and I've highlighted the Cox and Sherwood constraints here because they kind of do this to an extent. Both of them individually have a relatively high correlation in CMIP5, but they point to different answers. One points to a lower climate sensitivity, one points to a higher climate sensitivity. Then taking aside whether our reasons for believing either of these constraints, we then need a framework for incorporating these two pieces of information which ostensibly disagree into an underlying framework. And Danny Williamson's done some really nice theoretical work on how one might use this kind of information. So if our ensemble was perfect, we would call the models exchangeable with reality. So, but there's lots of reasons to believe that that's not in fact true. The models are approximations of reality. They run at a finite resolution. They have parameterizations in them, which we know to be simplifications. So we know that they're not absolutely exchangeable with reality. But how do we actually put a number on this? And so this is where Danny's paper sort of said, well, this is up to scientists to come up with a number. So the question is, how do we think about that? So again, to pick on one of Peter's papers, because he's here. When you're faced with an emergent constraint like his 2012 paper, where the future response of the future response to the carbon cycle of the tropical carbon cycle to warming is constrained by the seasonal cycle. It's a stunningly good correlation, and so there are two, but there are two things which you can take from this. It seems on the face of it, it would seem unlikely that you could get such a strong correlation entirely by chance. But it's possible that what we should be really taking from a relationship like this is that is there an underlying relationship in the construction of the models, which is effectively meaning we're dealing with a much lower, much smaller degrees of freedom than we might think we are with a multi-model ensemble. And so if all of the models have the same core ensemble, the same core parameterization for respiration or photosynthesis, are we really just seeing the parameters of that equation with 1 or 2 degrees of freedom being varied, and that's why we have such a strong relationship. And so this comes down to the very nature of what we mean by structural uncertainty. So it's possible for a constraint to be statistically robust and for it to be mechanistically valid, but still overconfident if the core equations in all of the GCMs use the same simplistic assumption. This is known to be the case in PPEs, and so back before even the word emergent constraint was coined, people were producing what we would now call emergent constraints with PPEs, that they were finding relationships between variables, potentially observable variables in parameter ensembles and climate sensitivity. But if you then apply those relationships to the CMIP archive, you can then demonstrate that they don't hold. Those relationships are too tied to the structural assumptions which are present in one GCM. And so there we have an out of sample test of the structure of the underlying structure of an emergent constraint. So the question, and it's a much harder question, is that how do we do that for CMIP? How do we test whether CMIP is an adequate sample of structural diversity for the question that we happen to be looking at? And so to get at this, one thing I'm proposing might be useful is to break down emergent constraints into a few different types, because I think that different rules apply to different types of emergent constraints.
2 minutes, Ben.
Say again?
2 minutes, mate.
Okay, so broadly, signal detection, feedback isolation, and frequency substitution. For signal detection is what might be in the past have been called detection of a climate signal in the detection attribution literature. So that's where you have a system where you're observing transient change and you're predicting further transient change in the future. It's the same processes. And to some degree, we don't care what the feedbacks are in those processes. If we can observe the TCR of the system, albeit with some noise today, then we can project that out into the future without knowing what's going on under the hood, unless there's something there's some common nonlinearity in the models which is missing. So if there's a permafrost bomb in the models which all of the models are not representing, then that would break this. But in general, this kind of constraint is relatively structurally robust. The second kind of constraint is to isolate feedback processes. So the Sherwood constraint, the Bryant constraint are classic examples of this, where you isolate the process responsible for the primary degrees of for the variability in the process you're interested in, and then look for processes, observable processes, which would correlate with that. And so this kind of constraint introduces possible additional structural errors, both in terms of the way that the process is parameterized, and if that's done in a common way in your ensemble. And so if there are, for example, in convection schemes in GCMs, if the same kind of ideas are repeated through different GCMs, then we have ourselves open to there being common structural assumptions in one convection scheme. And also our ability to sample other feedbacks in the system. So if the fact that stratocumulus feedbacks dominate CMIP5 variability doesn't necessarily extend to CMIP6 if there's different processes which are responsible for the shift in climate sensitivity in CMIP6. So we only, the emergent constraints only tells us about the ensemble we have. It doesn't necessarily, we shouldn't necessarily talk about emergent constraints as being real or not. They're always tied to a ensemble and a sample in an ensemble. And finally, and I'm going to run out of time, but the third constraint is frequency substitution. So that's why you have one you have one system, but then you excite it with a different type of forcing. So, for example, you excite it with the seasonal cycle rather than a transient forcing, and then you use one to constrain the other. And this kind of constraint, so the Peters constraint from climate variability and the Hall and Q classic constraints on sea ice come into this category. But then there's additional structural errors which come into this because there's potentially different feedbacks which make up the predictor and the thing you want to predict here. You have to consider not just the processes which might be missing, but that there might be different processes missing for the predictor and for the thing you're trying to predict. So, for example, for the photosynthesis, for the carbon cycle tropical constraint, you might be misrepresenting fire in your representation of the seasonal cycle today, but all your models might be missing phosphorus limitation, and that biases your future projections. So you need to account for potential structural errors which arise both in the predictor and in the predictand. So I'm going to skip the simple example and come to the summary, which is that we're really dealing with, when we talk about weighting schemes and emergent constraints, we're really dealing with a two-dimensional system. On one axis, we talk, it's the strength, the degree to which we're weighting models and distinguishing between models. And on the other axis, it's the selectivity of the weightings. That's how targeted the aspects of the weighting are to processes which we know to represent feedbacks in our ensemble. So down in one corner, we have model democracy. We have conventional weighting schemes where we're potentially weighting a lot, but we're not really paying attention to what's in the weighting schemes in terms of distinguishing between models. And up here in the corner, we have univariate emergent constraints where we've tied all of our we have all our eggs in one basket associated with one process. But also, the further we go up into the corner of this plot, the more we're exposing ourselves to structural errors by being being strongly conditioned on one structural assumption. So the question is, can we find a middle ground? And I'll stop there, leave my summary slide up because I'm out of time.